So it's always fun to come up with new and different ways of teaching a subject. And so today I want to show you something that I was thinking about the other day. I was trying to think of a different way that I could teach the 2x2 matrix and 4x4 matrix version of complex numbers and quaternions using colors. So that is what I'm going to do here. I'm going to show you a way of thinking about these two different matrices using various different colors. So let's start with the complex numbers. Okay, so complex numbers, in the way that I am teaching complex numbers, forms a 2x2 matrix. So the complex number has a real component, which occupies the forward diagonal of the 2x2 matrix, and you have the imaginary component that occupies the backward diagonal of the 2x2 matrix. Okay, the forward diagonal has the same sense, and the backward diagonal has the opposite sense. And so I decided to color code this complex number by making the real component black and the imaginary component white, so you can clearly see that the forward diagonal is real and the backward diagonal is imaginary just at a glance. Now there's another feature, there's another component to the 2x2 matrix in that the forward diagonal has the same sense in terms of positive and negative, and the backward diagonal, the real component, has the opposite sense in terms of positive and negative. Okay, so this is a really nice schematic, I think, of the complex number because it shows the incommensurability of the complex number. Okay, so in the beginning was darkness, and the creator said, "Let there be light." And so that's just a teaching tool. I use that as a teaching tool in the beginning. I use as a teaching tool just to, it might help some people remember. And so the darkness is on the forward diagonal and the lightness is on the backward diagonal. And the forward diagonal has the same sense and the backward diagonal has the opposite sense. Okay. So the complex conjugate of this is this. So the forward diagonal is still real, the backward diagonal is still imaginary, the forward diagonal is still black, the backward diagonal is still white, but the sense of the imaginary component has changed. So this way the positive is in the right upper right corner and negative is in the lower left corner, and in the conjugate of that, the negative is in the upper right corner and the positive is in the lower left corner, and so these two are flipping places. Okay, so yeah, so that is the difference between, this is how I depict the complex number and the complex conjugate of that number. Okay, so you see the positive and negative can flip back and forth, and that is the operation called the complex conjugate. It is really just a flip. You can think of it as a flip about the real axis. So even in Cartesian coordinates, the complex conjugate of that is a flip about the real axis, and here it is a flip about the real diagonal. So you can see that the complex conjugate, it has flipped about this diagonal. So that's another way of looking at complex conjugate. Okay, it is a negating, so you're negating that to get negative and you're negating that to get positive, so minus times minus is positive. Okay, and or you can think of it as the incommensurate of this. Okay, and or you can think of it as the complex conjugate. So that is the complex conjugate. It is the negation of the imaginary component. And it is also a transpose. So in a transpose, what you do is you take the row and you make it the column. Okay, you take the row and you make it the column. So you take the row that used to be plus plus, and you make it the column. Now the column is plus plus, and here the row is minus plus, the row is minus plus, and now the column is minus plus. Okay, and so that's called a transpose. And so the complex conjugate is the negating of the imaginary component, which is also referred to as a transpose. Mathematically, we are merely negating the imaginary component. So negating the imaginary component and the complex conjugate and transpose are all ways of thinking about the same thing. In general, though, we are just negating. So when you think of complex conjugate, think of negating these two components, the imaginary component. Complex numbers have very specific rules. Okay, so here are the two main rules of the 2x2 matrix version of complex numbers. Okay, so 1 times 1 equals 1. Okay, so when I put 1 in brackets, what I mean is the matrix, the 2x2 matrix. 1 in the 2x2 matrix is ones on the forward diagonal. Okay, so when I put 1 in brackets here, what I mean is ones on the forward diagonal, and they are the same sense. So they are either positive or negative. If one is negative, this one has to be negative. And so when you put positive ones on the forward diagonal, and you take positive ones and put it in the forward diagonal of a second matrix and multiply them together, when you square 1, you get 1. So in other words, you get ones on the forward diagonal. Okay, so 1 times 1 equals 1. Now I is different. Okay, I is positive and negative on the backward diagonal. Okay, so so if I took 1 and minus 1 and made the other two 0, so if this right here is the same as I. So when you see when I write I, and algebraically, to simplify the writing, if I write I and I put it in square brackets like this is my notation. This is the notation that I adopted based on what Robert Distinti is doing. Okay, so I like this notation. This is the notation that I'm using. And I'm not going to give it a name. I'm not going to call it the Distinti notation. I'm just going to call it, I'm just going to tell you what it is. So when you see square bracket with an I in it, I am talking about this matrix here with a 1 in the upper corner, upper right corner, a minus 1 in the lower left corner, and zeros everywhere else. So when you take I and multiply it by I, when you take this matrix and square it, you get minus 1. What does that mean? That means you get minus 1s on the forward diagonal. So when you take this 2x2 matrix and you square it, you get minus 1 in the forward diagonal. So that is the true meaning of I times I equals minus 1. Yes, I is defined as the square root of minus 1, so it's logical that this would make sense, but this is a kind of a proof of that assumption. So it's a proof of that when you multiply this 2x2 matrix together, you get minus 1 in the two-dimensional coordinate system, that the xy real imaginary coordinate system that that this describes. Algebraically, the 2x2 complex matrix looks like this. So algebraically, you would write A plus BI, and in the 2x2 matrix form, it looks like this. So the forward diagonal, the black, has the same sense. A goes, so if you had this equation and you would plug A into the forward diagonal and you would plug B into the backward diagonal, and B would have the opposite sense in these locations in the matrix, and A would have the same sense in the forward diagonal of this matrix. And so A plus BI is A. Okay, so A is on the forward diagonal, and when you take A by itself, okay, A is on the forward diagonal, and of course the imaginary component is 0 because we haven't put that in yet. And then plus BI, So instead of plus bi, you could just say a plus b, where a is on the forward diagonal and b is on the backward diagonal, and a has the same sense and b has the opposite sense. So this is a plus bi, a plus, this matrix plus this matrix equals this matrix. So the a and the b coexist in the 2 by 2 matrix, and they don't interfere with each other, and they each play a different role when you do mathematical operations on these values, or if you apply transform to this matrix. And in polar coordinates, the 2 by 2 matrix looks like this. Now here you have, this is Euler's formula equals cos of theta times I sine of theta. Okay, assuming t means theta, t is sometimes time. So cosine is on the forward diagonal in the black region, and it has the same sense. In this case, it's positive. And the imaginary component, so the sine sits in the backward diagonal of the 2 by 2 matrix in the white part, and it has opposite signs. So it is simultaneously positive and negative. So the imaginary component is simultaneously positive and negative. The real component is either positive or negative. The imaginary is both positive and negative. And of course the complex conjugate of this would be if I put a negative here and a positive there. And so that would, this is called a rotation matrix. This is a transformation matrix. Okay, cos theta plus I sine theta. This is the algebraic expression of the 2 by 2 matrix. And this matrix is primarily used for generating rotations. It's a transformation. It is a rotation matrix. So depending on what you put in for theta, if you want an object to rotate about a Cartesian origin, about some axis sticking out of the page, then you would use this transformation matrix to generate a counterclockwise rotation if positive z is pointing towards me. So that is a convention. It's just a convention. This is the convention that I'm using. But if you want to do a clockwise rotation, you would want to put a negative here and a positive here. And then you would get a clockwise rotation about an axis pointing out of the screen towards me. So I call that positive z. So if positive x is towards the right and positive y is up and positive z is towards me, I've shown this in other videos, so you can go back and look and see how this works with my computer program. But so I'm able to prove that this works and generates a counterclockwise rotation, a certain number of degrees, and you would put that in here for theta. So if I want to step 10 degrees counterclockwise, I would put 10 degrees in here. And of course, I would have to convert to radians. So the color coding of complex numbers in this manner, I think gives a good visual for lots of things that aren't really noticeable when you are reading an algebraic equation. So clearly you can see, first of all, the incommensurability of the forward diagonal and backward diagonal really sticks out like a sore thumb. Okay, so I think that is the main sort of objective of doing this kind of color coding, is it makes it very clear that there's something different between the forward diagonal and the backward diagonal, something significantly different that has of great importance, because the forward diagonal serves a different purpose than the backward diagonal. The forward diagonal is primarily a scalar. It cannot rotate. And although the backward diagonal can also do scaling, it is responsible for rotation. So if the backward diagonal is 0, there aren't going to be any rotations. Okay, you're not going to be rotating, you're just going to be scaling. So there's an incommensurate difference between the forward diagonal and the backward diagonal. They occupy different locations in the 2 by 2 matrix. they coexist without interfering with each other, and they work together to create beautiful images that that I call the Mandelbrot set, that people call the Mandelbrot set. And the reason I'm so interested in this is because of the way that the Mandelbrot fractal looks so similar to objects that we see in nature. Okay, so this is why I am pushing these complex numbers so much, because there's a lot of insight I think can be gained by studying the complex numbers, not just in terms of what they do, but in terms of what they are. Okay, I think we can get a lot of insights into how the universe works by studying how these complex numbers work and how they interact, but not interfere. They interact with each other, but they don't interfere. And they can create these amazing fractal patterns that are reminiscent of objects that we actually find in nature. So now what I'm going to do is I'm going to colorize the Quaternions. So I'm going to apply a similar kind of a logic to the Quaternions. Now the Quaternions, the complex numbers, they have a plus bi, but the Quaternions have a plus bi plus cj plus dk. So instead of one imaginary components, Quaternions have three imaginary components. So what I'm going to do is I'm going to colorize the Quaternions. What I'm going to do is I'm going to take the white. Okay, I'm going to instead of just using white, one color for the imaginary component. Now we're going to have three imaginary components. So we're not just going to have an I. We're going to have an I, J, and a K. So I'm going to colorize them red, green, and blue. Okay, I'm going to use the RGB, red, green, blue. Okay, so here is what a Quaternion looks like. This is just a Quaternion. There's actually multiple solutions for the Quaternions, and this one, actually I wrote a computer program to spit out a Quaternion that satisfied the rules of Quaternions, and this is the first one that popped out, and this is the one I've been using. So in all my software where I'm testing the Quaternions, I'm actually using this matrix here. And so what we have here, so in the 2 by 2 matrix, we had the forward diagonal was the real component, and we painted it black. So here the forward diagonal is the real component, real is black, only now the forward diagonal has 4 entries instead of 2 entries. Okay, so now in the complex numbers, the backward diagonal was painted white, and it had both positive and negative sense built into the diagonal. And so, B, this is B, so this is A plus BI, so this is B here. So in the Quaternions, okay, in the Quaternions, the I occupies the red region. So now I'm splitting out the imaginary components into different colors. So red is I, okay, and you can see that it has opposite sense. So it has entries that have opposite sense on the backward diagonal, okay, or in the locations. So it's got positive, negative, positive, negative. So now that's I. So now J is in green. So in this matrix, green is on the whole backward diagonal, but you can see it has both positive sense and negative sense. So here J is simultaneously positive and negative. And then we take the K, which I painted in blue, and it occupies the leftover places in the 4 by 4 matrix. So it is here and here and here and here. And as you can see, it also has simultaneously positive and negative sense. Okay, so this is how you spread out the imaginary into 3 imaginary components. They occupy the real, the I, the J, and the K occupy different locations in the 2 by 2 matrix. They occupy very specific locations. Okay, they're not just any location. These specific locations, okay, give us the rules. Give us the rules. And so the rules of quaternions are very similar to the rules of imaginary numbers. Okay, so you've got 1 times 1 equals 1. Only in this case, the this bracket here, which means matrix, is now we're talking about a 4 by 4 matrix instead of a 2 by 2 matrix. So 1 times 1 equals 1 means that when we put ones in the black locations, when we put positive 1, positive 1, positive 1, positive 1, and zeros everywhere else, and we square that, so we multiply it by itself, we are going to get positive 1. And so also if you put negative 1, negative 1, negative 1, negative 1, and you square it, you're going to get positive 1. Similar to the imaginary numbers, when you take I, and now I is red. So now I corresponds to these 4 locations in the matrix. That's all one number, that's I. Okay, so I times I equals negative 1. In other words, when you take, if you put a 1 here and a 1 here, so positive 1, negative 1, positive 1, negative 1, and made everything else 0, and you square it, you square the matrix, you're going to get minus 1 on the forward diagonal. Okay, and same with J. So J is green. So if you put 1, 1, minus 1, minus 1 in the matrix and made everything else 0, and then you squared that, you made another matrix the same and you squared it, you're going to get minus 1 on the forward diagonal. And same with K. So K is in blue. So if you put plus 1, minus 1, minus 1, plus 1 into a matrix, and you did that to another matrix, so you have 2 matrices that are the same and multiply them together, you're going to get minus 1s on the forward diagonal. So I times I is negative 1, J times J is negative 1, and K times K is negative 1. So these are all behaving as if they are the 2 by 2 matrix imaginary numbers. So they're behaving the same in that they put negatives on the forward diagonal when you square them. Okay, so there are more rules because this is now a 4 by 4 matrix, and we have 2 other entities, C and D. There's more rules than just the imaginary. So here are all the rules. The rules are really just, 1 times 1 equals 1. Okay, 1 times I equals I, 1 times J equals J, 1 times K equals K, and vice versa. So I times 1 equals I times I equals minus 1. And now we get, so that's the 2 by 2 matrix complex numbers. Those are the rules of the 2 by 2 matrix complex numbers. And then that's all there are. But for the Quaternions, you have a bigger matrix. So now you have to be able to multiply I by J. And so when you take, so I is in red. Okay, so if you put positive 1, negative 1, positive 1, negative 1 into a matrix and make everything else 0. Okay, I times J, so J is green. So then if you take another matrix and you put positive 1, negative 1, negative 1, if you put that into another matrix and make everything else 0, and you multiply them together, you are going to get K. And K is everything in blue. Okay, so I'm going to do an example. I'm going to show you how this works just so you can see it in real life. I'm just going to do one case, and then we can assume all the other cases work, or you can test them out for yourself. So here is the online application software that I use to multiply matrices together. And I'll make sure to put a link to this in the description so that you can test this out yourself. Okay, so what we're going to do is we're going to make a matrix. We're going to multiply I times j, so we're going to take the I matrix, the red matrix. Okay, we're going to put positive 1 here and negative 1 here, and positive 1 here and negative 1 here. Okay, positive 1, negative 1, positive 1, negative 1, and we're going to make everything else 0. So now we have a matrix that only contains I, the imaginary component. Okay, so now we're going to set the other matrix up. So we're going to do I times j. J is green, so we're going to put a plus 1, minus 1, minus 1 into the second matrix. So we're going to do plus 1, minus 1, minus 1, and we're going to set everything to 0. So now we have, in 4x4 matrix format, we have I times j. Okay, so I'm going to calculate that, and what we end up with is 1 minus 1 and minus 1, 1, which just happens to be the blue plus minus plus minus. Okay, so we've shown that I times j does in fact equal k. Now, one thing I want to point out here that you can see clearly from the chart, and I'm not going to do an example, but I'm going to leave it to you if you want to prove it. Okay, so I times j is equal to k, but j times I is equal to minus k. Okay, so what that means, that the 4x4 matrix version of complex numbers, i.e. quaternions, are not commutative. A times b doesn't always equal b times a. Okay, I times j does not equal j times I. It equals the negative of it. Okay. In other words, complex numbers are commutative because you can see in this section of the table, which is the just the 2x2 complex, the rules for complex multiplication. So 1 times 1 equals 1, and 1 times 1 equals 1. I times 1 equals 1, and I times 1 equals 1, and I times I equals minus 1, and I times I equals minus 1. So the complex numbers are commutative. It's only when you start adding dimensions that you lose the commutativity. So, you know, I times j is not equal to j times I, and j times k is equal to I, and k times j is equal to minus I. So it's only when you expand beyond the 2x2 matrix complex numbers, the 2x2 complex numbers, do you lose some of the rules, i.e. the commutativity of the number system. Here is what the quaternions look like in polar coordinates. So this would be Euler's formula in the 4x4 matrix version of quaternions. And so as you can see, the cosine, the black region, occupies the forward diagonal of the 4x4 matrix, and it has the same sense. And everywhere else, as you can see, everywhere else is sine. Okay, so on the different other locations, so in I, in the red, you've got plus and minus, plus and minus. In the J part of the matrix, in the green, you have plus sign, minus sign, minus sign. And in the K region of the matrix, you have plus sign, minus sign, plus sign. So this is something I showed in a previous video. I showed you my code for how I rotate points about an arbitrary axis in using this particular matrix. Okay, so if you want to find out, if you want to see an example of how this is done, I will put a link to that video in the description, because I give you a concrete example of how this can be used to rotate a point about an arbitrary axis in three-dimensional space. Finally, I just want to talk a little bit about convention, because I often get the question, why do I use a different convention than the mainstream? And so the main reason is because I can. If the output is functionally identical to what is expected, then one convention is not better than the other, it's just different. And so as I said before, this is the 4x4 quaternion matrix that I found using a computer program, and it satisfied all of the rules for quaternions. But this is the one that is most popular. This is the one that pops up when I do a search for the matrix version of quaternions. And so here's a little sketch, blackboard sketch of it. And so you can see that the pattern is just a little bit different. You've got the four diagonals still positive, but the green and the blue have switched places, and the one on the right has is the negative sense, so it is the transpose of the one I was using. And so, but both of these matrices produce a counterclockwise rotation in the standard that we're using. So that creates a right-hand rule counterclockwise rotation. And so see, these are just two quaternions. Now if I wanted to switch my convention, so I could take this convention here and flip everything about this axis here. And if I did that, then I would end up with the complex conjugate. Mine is almost the complex conjugate of this, only my red or my blue and my green are flipped. And so if I use my convention and I put green here and blue here, so this would be real I, J, and K, so red, green, and blue. So if I switch the green and the blue, then I'm going to have the complex conjugate of this one here, and then what's going to happen is my default rotation is going to be now clockwise. So I would, if I switch the green and the blue in these in the upper right corner and the lower left corner, then I will have the complex conjugate of this, and the default rotation will be clockwise. So flipping the green and the blue here, well, having the blue in this position and the green in this position creates a counterclockwise rotation. And but if I switch them, then my default would be clockwise. So that's all about convention. If I wanted my default rotation to be counterclockwise, I would use one of these two. If I want it to be clockwise, I would use the complex conjugate of this. So to recap, I thought it would be interesting to try to explain complex numbers, the 2x2 matrix form of complex numbers, using a color code. So for the complex number, we have black and white, and we have the forward diagonal is black and the backward diagonal is white, and the forward diagonal has the same sense in terms of plus and minus, and the backward diagonal has the opposite sense. Then we expanded the white, the imaginary component of the complex number, to have three components. Okay, to have three components, which we called red, green, and blue. Red, green, and blue. And we placed the red, green, and blue into the 4x4 matrix to create a quaternion, which can be used to rotate, could be used to create a transformation matrix to rotate a point in a three-dimensional space. People often ask me what these matrices are useful for. What's the point of learning them? What can they be used for? And of course, they are primarily used, especially quaternions, are primarily used in computer graphics to perform rotations of objects in 3D space. And but they are also useful in many other fields of electrical engineering and in physics, of course, and in other fields that require higher dimensional complex numbers. So that's all I'm going to say for now. I'm hoping that this approach to colorizing the complex numbers and the quaternions can give you further insight into the inner workings of these two mathematical objects. And I know that, understanding complex numbers can be very difficult if they're not presented to you with the correct language. And some people just think better in colors than they do in symbols. I know some people have trouble processing algebraic symbols. And so I'm hoping that this approach might help the people that struggle with that sort of thing to give them some further insights into how these matrices actually work and how this is actually a better way of thinking about complex numbers and quaternions in terms of transparency and just in terms of being able to understand what is going on. So that's it. I hope everyone had a great weekend, and I will be back.